All right, we're going to take a look at another example from lesson 17 where we are taking a in-depth look at rotational dynamics. Here we have a string wrapped around a cylinder of mass m and radius r. The end of the string is held and the cylinder is released. What is the acceleration of the cylinder's center of mass? Previously, we were looking at how the rotation of the cylinder affected how a mass was able to drop off of its side as it unwound a cord. Now we're looking at how does that unwinding of a cord affect the movement of the cylinder. We do need to coordinate our axes and our positives and that kind of thing. We are going to let counterclockwise rotation in our picture be positive, and we are going to also let the motion downward to be positive. That will help us in the long run. So we're going to go and look at a solution. So this solution is already laid out for you. The big thing is that you start with applying Newton's second law. We're going to start with applying Newton's second law the normal way. All right, we're looking at the fact that the sum of the forces is equal to the mass times the acceleration. The forces acting on this is the weight down and the tension up. Our weight in this case is positive and our tension is negative because we set down to be positive, so that is a little bit different. Because it is going to accelerate downward as it falls, my right-hand side is positive as well. So we end up getting this relationship. We are not going to know the tension, and we generally want to get rid of that, so we need to find a way to pull that out of the equation. In order to do that, we're going to apply Newton's second law, rotationally speaking. So we are going to look at the sum of the torques is equal to the moment of inertia times my angular acceleration. Same formula we've been applying before. We're still dealing with a solid disk here, or a solid cylinder, and the moment of inertia of that shape is this. And angular acceleration does translate to our linear acceleration with this formula. We will use both of these here and here, which is what gives us this lovely long version over here. My left-hand side is the torque provided by the force of tension and the torque provided by the weight. My tension acts at the radius from the center of my object. It's going to still spin about its center as it falls. My weight acts at the center of the axis of rotation, so it's going to not do anything. All right, it's not going to provide any torque. So that's what we have going on here. We are able to simplify that out because if the weight doesn't do anything, that term goes away, and sine of 90 degrees is 1. That's why we have R times the force of tension is equal to the 1/2 mr squared times a over r. That does simplify because this r will cancel with one of these, and then I have one r on both sides, and those cancel to give us this. You'll notice I have labeled my two equations, equation 1 and equation 2. We do put this equation into this one, and that gives us this lovely equation. So my weight of my cylinder minus 1/2 ma, we got over here, is equal to the mass of our cylinder times its acceleration. We are going to look at solving this for the acceleration, so we move this over to the other side, and we do see that the acceleration here is going to be 2/3 that of the gravity. So this is going to drop to the ground a lot more slowly, unwinding, than if we were to just let it fall on its own. I will tell you, you will use this in a lab later, so pay close attention and see how you might use this to solve some other bits of information about what this is doing.